So at present, all of the bonds that we've looked at in detail have just been what we describe as single bonds. These are where we just have a single pair of electrons between our two atoms that are being bound together. It is also possible to share larger number of electrons and form what we call double and triple covalent bonds. So single covalent bonds involve the sharing of 2 electrons, double covalent bonds involve the sharing of 4 electrons, and triple covalent bonds involve the sharing of 6 electrons. So in water, which we looked at previously, there are 2 single bonds to the oxygen. If we look at something like nitrogen, N2, it turns out that there are 6 shared electrons. Remember that we can replace each pair of shared electrons with a line, so we would put 3 lines in there to indicate that 6 electrons are being shared, and this is a triple bond. When we go to something like oxygen, O2, each oxygen atom, this is actually, I should fix this a little bit. Each oxygen atom in group 6A and has 6 electrons around it. When these guys share their electrons, turns out that we end up with, I have to just remedy this a little bit, a double bond between the 2 oxygen atoms. So these are the possibility for covalent bonds. We don't see quadruple bonds with 8 shared electrons. So when a pair of atoms shares 2 electrons, we call that a single bond. When a pair of atoms shares 4 electrons, we call it a double bond. And when a pair of atoms shares 6 electrons, we call it a triple bond. We're just going to have a look here now and see how the number of valence electrons that an atom has is related to the number of covalent bonds that it forms. So we looked at this previously, but we're going to examine this in a different sense. The first thing to recognize is that if an atom is going to form a multiple bond, that is a triple bond or a double bond, then it has to have, at the very least, 2 octet vacancies. And what that eliminates is that the group 7 elements with only 1 octet vacancy and hydrogen with also only 1 octet vacancy will never form a multiple bond. So that's kind of fun. The other thing is, because hydrogen only has the 1 octet vacancy, it can only form 1 connection to another atom, so it's always going to be on the outer edge of a molecule. It can't ever be in the middle of a chain, because the atom that goes in the middle of the chain has to be able to form at least 2 bonds. Similarly with our atoms in group 7A, they're going to tend to be, so say like fluorine, they're going to tend to be on the edges of molecules, not in the middle, because to be in the middle, you need to be able to form at least 2 bonds. So group 6A, all of the atoms that are in here have 2 octet vacancies. Covalent bonding only occurs for the nonmetals, so we're just going to focus on the nonmetals. So common bonding patterns for the atoms that are in group 6A is to form 2 single bonds or 1 double bond. These guys can't form a triple bond. When we go to group 5A, these atoms have 3 octet vacancies. So they like to make 3 bonds, and they can do this in a whole variety of ways. They can form 3 single bonds, they can form a double bond and a single bond, or they can form just the 1 triple bond. So elements that are in the nitrogen group have more diversity to their bonding than elements that are in the oxygen group. They can just do more stuff. Now when we go to group 4A, what we see is that our carbon atom here has 4 octet vacancies, and this opens up a whole wide array of possible bonding patterns. There can be 4 single bonds, there can be a double bond and 2 single bonds, there can be a triple bond and a single bond, or there could be 2 double bonds. And that's why we have a whole branch of chemistry called organic chemistry that deals with the chemistry of carbon-containing compounds, because carbon is so versatile in the way that it can form bonds. It's also why carbon is such an important element in biochemistry, because it's just kind of it kind of does everything. Yeah. Okay, so covalent compounds form when atoms share valence electrons so as to allow each atom to have a share of 8 electrons. We can talk about the concept of octet vacancies, and this is the number of unpaired dots that an atom has in its Lewis symbol, and this is a useful predictive tool for guesstimating the number of bonds an atom likes to form in order to achieve an octet. Now, it's not 100% foolproof, but it's a good guide as to the number of bonds that a particular type of atom will form. Okay, so we actually skip over section 7.14, and then I reverse the order of 7.15 and 7.16. So just bear with me here, and I think it's for a good reason. Everything we've been doing so far, we've just been kind of looking at our atoms and thinking about what is the logical way for these guys to come together. How are they going to logically share electrons so that every atom gets an octet? And that works for simple molecules. But after a while, it gets a little bit klutzy, and it's not always intuitive. So what have been developed is a series of systematic steps for making sure you get the correct Lewis structure for a covalent compound. So the first thing we should realize is that in a Lewis structure, we're assuming that the total number of valence electrons is what the molecule is going to use to hopefully ensure that every atom has a share of 8 electrons, or 2 if it's hydrogen. So what we're going to do is we're going to pull all of the valence electrons together, and then we're going to try and attempt to distribute them so everybody gets a share of 8, or the widow atom hydrogen, it gets its share of 2. So the first thing that we're going to need to do is tally up the total number of valence electrons that we have, and just all you have to keep in mind here is that the group number for a non-metal element is equal to the valence electrons that atom has. So if I have this compound here, carbon tetrachloride, I've got 1 carbon, and that has 4 valence electrons, and then I've got 4 chlorines, and because these guys are in group 7A, they each have 7 electrons. So adding that together, 4 plus 4 times 7, or 4 plus 28, gives me 32 valence electrons. So what I've got to do is figure out, how do I share these guys so that each of the 5 atoms in carbon tetrachloride ends up with an octet. Okay, so once I've got my tally of electrons, what I want to do then is get the basic arrangement of atoms. What we're going to have is 1 atom that goes in the middle, and a bunch of atoms up to 4 that go on the outside. Now, we've already seen that hydrogen's always an outer atom. So that can sometimes help. It doesn't help us in the case of carbon tetrachloride because there's no hydrogen, right? But it would help us to know that this is going to be the arrangement of atoms in something like water, H2O, right? We know that the oxygen's got to go in the middle. But here's the guideline. The element with the lower group number will be the central atom. because it needs to form the most bonds to get to an octet. Remember that carbon needs to form 4 bonds to get to an octet, but and carbon's in group 4a, fluorine only needs to form the 1. Now sometimes you'll have a compound where your atoms are in the same group. So sulfur dioxide, sulfur's in group 6a, as is oxygen. So what do you do then? Well, if they're in the same group, the element that is lower down in the group, that is in the higher period, that's going to be your central atom. So in this compound, sulfur goes in the middle and oxygen goes on the outside. So in our example here, carbon's in group 4a, chlorine's in group 7a. So that tells us that how we're going to organize things is carbon being the central atom, and then the chlorines are going to be the outer atoms. So step 1 was count up electrons. Step 2 was determine arrangement. So now all we have to do is figure out where do our lone pairs go and where do our bonds go. And remember, we've got 32 electrons to distribute, and we're going to try and do that in such a way that everybody gets an octet. So what do we got to do once we've determined the arrangement? Well, we're going to have to make some bonds. Right? And we're not going to have any kind of molecule at all unless we make some bonds. So we need at the very least one bond between each of the outer atoms and the central atom, or otherwise we don't even have a molecule. So our third step is to connect each of the outer atoms to the central atom via a single bond. And keep in mind that every bond that we draw in uses up 2 electrons. So we need to subtract that total number of electrons that we use from the total. So here we go, 2, 4, 6, 8. So we started with 32, and then we have to subtract 4 lots of 2 for each of the bonds that we drew, and that leaves 24 electrons to finish everything else off. So now what we're going to do is we're going to start adding lone pairs. And it's a pretty simple procedure. We're going to finish off all of the lone pairs, finish off all of the octets on our outer atoms with the lone pairs, and then if we have any left over, we'll finish off the octet of the central atom. So we're going to work from the outside in until we run out of electrons. So we're going to add lone pairs to complete the octets of the outer atoms, and then we're going to subtract from the total all of the electrons that we use. So we had 2 electrons in the bond, so then we'd need to add 2, 4, 6, another 6 electrons to each chlorine to complete each of the octets. So after making the bonds, we had 24 electrons left, and now we're going to add 6 electrons as lone pairs to each of the 4 chlorine atoms in order to complete their octets, and that leaves me with 0 electrons. So we're done. So we know that the chlorines have an octet. If the carbon doesn't have an octet at this point, we can't add in any more electrons. We're going to have to do something else. So the 5th step in the systematic process for drawing a Lewis diagram is after the 4th step, if you have any electrons left over, put them on the central atom. Now in this case, we don't. So step 5 is not needed, and many times step 5 is not needed. But if we had electrons left over at this point, we would add them in. So regardless of what happens, by the time you get to step 5, you will have 0 electrons left. At the end of step 5, you want to make sure that you have no electrons left. If you don't have 0 electrons at this point, you've done something wrong. Okay, so step 6 is to check if the central atom has an octet. 2, 4, 6, 8. If it does, there's nothing left to do. If it doesn't, you need to convert lone pairs to bonds until the central atom does have an octet. So I'll give you an example. Here's a structure where we have carbon bonded to one oxygen and one hydrogen. Now, in this arrangement, we would have 0 electrons left. When I check the octet around the central carbon atom here, 2, 4, 6, it doesn't have an octet, it's too short. So what I have to do is bring in a lone pair and turn it into a bond. And then now, my carbon atom has an octet, 2, 4, 6, 8. Now you can see I haven't added any electrons in, I just moved them from being a lone pair to being a bond. And so that's what we'll do in step 6 if we need to. Now in this case, carbon has a complete octet and step 6 is not needed. And that's quite typical. Many molecules don't have double and triple bonds. So now we're going to kind of look at one where we do need to use double bonds. So we're going to draw the Lewis structure for carbon dioxide. So step 1 was to count up the valence electrons. Carbon is in group 4a, so it contributes 4 valence electrons. There are 2 oxygen atoms and both of them are in group 6, so they each contribute 6 valence electrons. So 4 plus 2 times 6, or 4 plus 12, gives me that I've got 16 electrons to work with. Now I have to identify how my atoms are organized in space. So what atom is going to be the central atom is what I'm looking for, and what atoms are going to be on the outside. So carbon is in group 4, oxygen is in group 6, so therefore carbon is my central atom and my oxygens are on the outside. So I draw out my basic arrangement of atoms, and then I connect my outer atoms to my central atom with single bonds. Each of the single bonds requires 2 electrons, so I have to subtract 4 electrons from my total of 16, leaving behind 12 valence electrons to finish everything else off. So what I got to do now, I apologize this didn't convert too well from my older version of PowerPoint, is I've got to use those 12 electrons to finish off the octet of my outer oxygen atoms by adding lone pairs to them. So to each of the 2 outer oxygen atoms, I've added 6 electrons to complete their octet. So 12 minus 2 times 6, that leaves 0 valence electrons left. So in step 5, I would have added any leftover electrons to my central atom, but I don't have any. So after step 5, it doesn't look any different from after step 4, and I'm down to 0 electrons. And remember, I said it's very important that you check that after step 5, you've hit 0 electrons. You shouldn't have any left over at that point. So here comes the important thing for step 6. What I've got to do in step 6 is I've got to double check that my central atom has an octet. And if it doesn't, I'm going to bring in lone pairs until it does. So let's have a look here. The carbon has 2 4 electrons around it, so it is 4 short from having an octet. So what I'm going to do is I'm going to bring in those 2 and I'm going to turn them into a double bond. That doesn't quite get me there, does it? 2 4 6, I'm still 2 short, so I have to bring in another 2 and form a second double bond. So generally we'll bring them in from one atom at a time, and a good rule of thumb here was we know that oxygen in group 6a loves to form two double bonds. So we're going to kind of allow, or loves to form a double bond. So we're going to allow these, this structure is nice because it gives each oxygen the opportunity to form 2 bonds. So there are some things that we kind of see, all the time. If you've got a group 7 atom present, it's probably going to be an outer atom and it's probably going to form 1 bond. Oxygen, sometimes it's an outer atom, sometimes it's a central atom, but most of the time it forms 2 bonds. Nitrogen almost always forms 3 bonds and ends up with 1 lone pair. Carbon almost always forms 4 bonds and has 0 lone pairs. Now that's what we most commonly see, but it's not always the case, but that's what we tend to see pretty frequently. When you're not seeing these patterns, then that's okay, but just make sure to double check your work closely. Okay, so we went through some really systematic procedures for drawing Lewis structures in this video.